Today we're going to take a look at solid edge simulation. Even though the title of this presentation is solid edge simulation, but in reality we're going to be talking about your companies. How these tools can make your company more productive, shorten your design time to market, and react to market faster, quicker. So with that, let's begin. So first thing I'm going to talk about is agenda, obviously, what we need to cover today. We're going to talk about challenges that industry facing today as far as FEA analysis. We're going to talk about how companies like yours can gain advantage, competitive advantage using these tools. And then we're going to take a look at three supporting examples. We're going to take a look at simplified model analysis, how we can take advantage of tools available inside of Solid Edge because it's one single integrated environment. We're going to take a look at how we can take advantage of ability to extract thin wall bodies from your design, specifically if they're sheet metal parts, and take advantage of better performance, faster, getting faster to results. And then we're going to finally take a look at design optimization, how you can automatically optimize your design to save some material and reduce cost of your product. So if we take a look at today's landscape, a lot of companies facing challenges in this area. In today's face-based world, a design engineer has to wear multiple hats. Not only he needs to design the product, he needs to be responsible for how safe, how durable the products are. Outsourcing separates analysis from design process, thus inhibiting the true innovation and limiting the volume of analysis that can be done. Even if company has inside dedicated analyst, it's still a long log probably, and it's much faster, much more productive to perform analysis on at the earliest stage of the design than waiting the results coming from analyst. Sometimes today's simplistic simulation products out there provide inaccurate or incomplete results, leading to bad results. And finally, the big showstopper is lack of CAD associativity. Because let's face it, in today's world, you need to do a lot of what-if scenarios in your design. And if that link is broken, you're going to waste a lot of time transferring data from tool to tool and trying to minimize the time lost in the process. So solid edge simulation solves all these problems. First of all, it's a geometry-centric product that uses the same interface as a basic solid edge. It's easy enough for any solid edge user walk away from the product and come back and pick up where he or she left. So easy to use this tool that there is no really in-depth training required. Basically, person needs to understand some basic FEA principles, and he or she can successfully solve the problem at hand. So it enables engineers, designers perform their own simulations. More analysis gets done in less time. Your workflow is linear, and your product gets to market faster. The layout of a user interface is designed to guide users through the whole process, and you will see how it happens. So it makes it easy to learn initially and revisit if necessary, as I mentioned earlier. So what are some basic tools, some basic remedies inside of solid edge simulation that make it so powerful and so desirable for a lot of companies? First of all, any package out there requires ability to refine mesh, because refinement of a mesh is a really serious factor when you consider results, the accuracy of your results. So solid edge simulation provides means of defining mesh, even though it automatically does a really nice job of meshing components of your assembly you're trying to analyze based on their size, but you can fine-tune it further by defining specifically how many elements you want along the edge, how many elements you want on that surface. And the most important, this technology, meshing functionality, is based on FEA, and that is industry-proven product. We're going to talk about this a lot today because FEA is a flagship of our offering for stress analysis, and it's industry-proven tool. Full complement of realistic loads and constraints are defined and available inside of solid edge simulation. They are geometry-based constraints, thus they're easy to understand, easy to implement and set up for the model. Solid edge simulation provides such constraints as a fixed pin, no rotation, symmetric, cylindrical constraints, different loads, bearing, torque, weldments can be taken in account. It's again geometry based mechanical and temperature loads for thermal analysis. Conveniently, the tool that's used, and I'm going to repeat it during my presentation again, the tool that is used to define direction of force is a familiar concept inside of solid edge because it's a one single integrated environment. Solid edge simulation is uniquely positioned to solve your problems quicker and more efficient than other products. And the reason is simple, because some time ago, synchronous technology was introduced as disruptive technology in the market. It allows you to quickly change your parts without actually diving inside of a component and see results in FEA area. So it allows you to remove unnecessary features such rounds, holes, fillets, unnecessary for this particular analysis. Order-free design is blazingly fast. You're not facing any number of features that you need to figure out how the part was created in order to simplify or modify it for analysis. Applied loads and constraints are maintained during the model changes and even during the multiple what-if scenarios. We're going to take a look at this in a moment. And finally, we talked about this. Mesh refinements are applied automatically to a modified, refined geometry. So let's take a look at one of the examples. We're going to be analyzing this snow plowing machine. Let me switch to solid edge. That's what you see on the screen. This attachment where plow is attached via this pivot arm to a frame of a snow plowing machine. And obviously it exerts a huge deal of load on this particular pivot arm. And what we're going to do, we're going to analyze this and see how we can reinforce this particular design to withstand that load. First of all, it's a one single integrated environment, and I'm going to talk about this in a second. But before I do that, quickly within solid edge simulation, I can isolate with the display configurations. I can isolate all the required components for the analysis, and I can even take it further, because how quick you can set up your study and how quick you can get results really affects the bottom line. So with solid edge, we have ability to simplify the model, to remove unnecessary areas. In this case, not only I can select face by face, but I can select the whole feature. It saves me a tremendous amount of time and facilitates really fast and accurate results at the end of the simulation cycle. So then I can just tell the system to use simplified model, and I'm ready to start my simulation. I mentioned that it's one single integrated environment, so you don't have to dive into another product. It's all familiar interface. We're going to create new study. And one thing I like to point out, that solid edge simulation allows you to do linear static, normal modes, linear buckling, as well as heat transfer, steady state heat transfer analysis, and in combination with all the above. In this case, we're going to do linear static analysis, and also solid edge simulation provides ability to perform analysis on the solid bodies, on the surface bodies, and also in a mixed mode. So right now we have all the solid bodies. I'm going to start my simulation setup. And first thing you'll notice that how easy it is to set up. You're going to progress from top to bottom, or if you prefer to see the whole panel, you can progress from left to right. And right now we're at the stage where we need to define geometry. It's just simply a matter of selecting all the components that's supposed to be inside of that simulation study, and automatically information gets transferred to that study. As you can see, solid edge simulation knows all about the material. Steel automatically picked up from the parts, part level, but if you want to change that at any given point, you can access and edit material and remove the option to read the material from the part and define your own material. Okay, so now we're ready to start applying constraints. As I said, you can progress from left to right using this toolbar. And solid edge simulation provides structural loads, body loads, temperature loads for heat transfer analysis, constraints, full load of constraints, and connectors. We're going to talk about this in a couple seconds. First, I'm going to define the force. Solid edge is a really user-friendly environment. Same tool that we use to manipulate geometry is used to define the direction for the force. And also, one thing I'd like to mention, that it takes it's unit neutral solution. So I can type in any units, any format, and it will take it. So I'm going to progress from top to bottom. We defined the loads. Let's go define some constraints. We're going to make sure that we solve this bracket against, or this pivoting arm against these couple pins. They're going to be fixed. And one thing is that right now we analyze an assembly, so we need to let SolidEdge know how these components are related to each other. It's quite easily can be accomplished with connectors. Connectors can be applied automatically, manually. We can create bolt connector without actually having bolts. You can imitate bolt connectors between components, and edge connectors when it comes to surfaces and sheet bodies. So I'm going to conveniently select all the components, and just with one single click, SolidEdge takes care of all these connectors for me. I can look through visually and graphically. I can go through this list and see which ones are actually defined by the system automatically. I can select any one of them, delete or multiple. In this case, I'm going to accept everything that system gave me, and pretty much mesh and solve the model. You'll see another sign of efficiency of this tool. I can do this in one single step, mesh and solve. I can click on mesh and solve, and what happens, system takes into account all the boundary conditions, all the loads that defined in this assembly, and transfer them in an XNestron that behind the scene solve this and brings the results back inside of the window. So post-processing window is very important because that's your window into results. You need to be able to interrogate results and come to a conclusion if those are acceptable or change something in your model. You can probe different areas in your design, even show displacement. As you can see, chart populated with all these results, and you can select all these results, copy them, place in a spreadsheet for further analysis if you want to. You can take a look at different display options. We're not going to dwell on these, but all different options are available. You can animate your design and take a look at how your model performs under this stress. But what I'm interested here is in stress factor of safety. If I switch to factor of safety and define my own conditions instead of accepting the defaults, actually it's very important. That's a very important part. So I want to make sure that we are up to value of 4 or 5 for this particular results. And you can see the red shows me that some areas are still of concern. So I need to make changes. How do I make changes? Because it's a one single integrated environment, as I mentioned earlier, you don't have to dive into back into product and make changes. On top of that, Synchronization technology allows me to select the face and adjust values just on the fly. Something like this will do. Not only have to rely on dimensions, I can select the face and move it to the next position. Maybe that cutout doesn't need to be that deep. Let's adjust that. Maybe we can adjust that ear on the bottom, make it a little bit stronger. And I'm gonna just rotate this ear to make that ear a little bit thicker. So let's do something like minus 10 degrees. And overall, I'm gonna beef up the whole part, maybe by 10 millimeters. So you can see how easily I can make changes to the part because of Synchronization technology. This is really great tool that allows to change and quickly get results faster. So now what I do, I don't have to go again back to analysis tool. It's all right here. I can just select mesh again and say mesh and solve. Everything is applied automatically. All the boundary conditions, all the constraints, all the mesh options were defined. They are reapplied automatically, and system will process this assembly and gives us results really fast. So now we can see, if we take a look at actually factor of safety, let's go back and define again our conditions between 4 and 5. Now we can see that we're pretty much let me turn off these connectors. So we're pretty much green throughout, so we're good. Everything is pretty much at the factor of safety 5. So we accomplished our results. So you can see how easily I could accomplish my task and redefine this design to meet our goals without actually leaving the tool. Everything happens inside of SolidEdge. I'm using the same same familiar instruments, to some same familiar tools to manipulate geometry, and hopefully you see the value behind this, how quickly and efficiently you can be doing analysis and making changes and going through iterations. So let's go back. So we looked at this simplified analysis, simplified model analysis. Let's move on. Every package needs to have some means of defining constraints between different components, and SolidEdge does it really well. It allows you to connect, to define connections between components inside of assembly in many different ways. It can be linear contact, it can be glued connections. You have manual interface, user interface for face selection. If for some reason system doesn't give you automatic connectors, you can do it manually. And most importantly, system gives you automatic contact detection tool, and that's very important. To speed up results, to speed up the processing time, SolidEdge is positioned really well with the ability to analyze sheet bodies, especially if you're doing a lot of sheet metal design. Ability to extract mid surface is really out of this world, because you can apply this in any sheet metal design if you're doing a lot of that. And 2D shell element ideal for sheet metal analysis. Mid surfaces can be extracted on assembly level, and I'm going to show you how it happens. Sometimes you deal with plastic parts. It's suitable for manual extraction of mid surface and analyzing that way. So in this example, we're going to take a look at the lawnmower, and specifically we're going to take a look at structure that supports driver of that lawnmower. So let's open this assembly. First thing you'll notice that if I turn around this model, you'll notice that the load will be transferred from the seat through this sheet metal part into springs and into lower structure. So we need to analyze this structure and see if it can withstand the load of a driver riding in that seat. So again, using assembly configurations, I can easily isolate components on my screen, the ones I want to analyze. And before I even dive and start creating analysis, I want to show you really unique tools within SolidEdge. We can extract, because the ratio of thickness and the length of these parts is great, it could be really troublesome trying to mesh these thin wall parts, as you know probably from your experience. So mid-surface functionality allows to extract mid-surfaces from these parts on assembly level. If you notice, I'm doing extraction for all these three parts without actually diving into the parts themselves. So now when we show these surfaces, they all extracted at assembly level. It gives you really flexibility and speed analyzing your structure. So let's take a look. Now we're gonna start creating new study, and in this particular case, because we're dealing with the sheet bodies, we don't need to go with tetrahedral type of mesh. We can get away with surface type of mesh. And then again, as we did in the previous time, all we have to do is just select the parts that's supposed to be included in that study. Before I go any further, I would like to show you another really powerful way of extracting edges. Not only extracting edges, but splitting the face automatically. This is another huge productivity booster. Let's say in this situation where springs are pushing against that bar, we need to define more closely, more refined areas where the spring actually will apply loads. And so that allows you to offset edge, and not only offset edge, but split that face automatically with defined offset. How great that is. And now we're ready to start actually applying loads. As you can see, SolidEdge simulation automatically knows all about material thickness because we extracted mid surfaces in a legitimate way automatically. Okay, let's go and start applying loads. Again, everything goes from top to bottom. We're going to apply some force onto these surfaces, and we can do this on the multiple surfaces at once. Let's see, 300 pounds of force probably sufficient for a pretty big guy. We'll take care of that. As far as constraints are very flexible. Not only we can constrain face, we can points, we can constrain edges. So I can select the two bottom edges and constrain the whole assembly that way. Connectors, again, because we're dealing with assembly, we need to make sure that solid edge understands how they connected to each other. Quite easily I can define the search distance and select all the components. System automatically will find for me all the connectors, and graphically I can isolate them and find out which ones, actually, if those are the ones I actually want. One more things that I think that I'd like to point out is ability to refine your mesh. We talked about this. It's very important to be able to refine mesh for more accurate results, specifically around areas of stress concentrators. So in this case, I want to select the edges, and I'm going to select all these edges right here and define number of elements as 12. And then all we have to do, just mesh and solve. What will happen, that refined mesh around the stress concentrators will be taken in account first, and then a regular mesh slider value will apply. So you can see how quickly the results came back, and interestingly enough, solid edge simulation even shows you the thickness of the components, even though we're analyzing sheet bodies. So let's take a look at this. Let's animate this design, and you can see how the whole structure performs under this stress. So maybe the stress is too high and we need to reinforce this structure with a couple additional components. How would we go about this? First of all, solid edge simulation provides you ability to go through multiple studies and quickly go through what-if scenarios. And I'll show you how it happens. I can select this study, copy, and paste. I can select and paste only elements, single elements of this study, such as loads, constraints, mesh, but in this case I want the whole study. And let's go and add a couple more components to our study. Again, I'm going to go into mid-surface functionality and extract mid-surface from this additional couple components. You can see how quickly and easily I can do that. And now we can identify geometry. You don't have to redefine anything. Everything is redefinable on the fly. I can quickly select additional components that I want to include. I'm pretty much done. As far as constraints, I don't have to do anything else. I told you that constraints and loads are very flexible. As you can see, we define our edges, but we can add faces in the equation. In this particular case, it's relevant to add couple faces here. And finally, for the connectors, we again can go after automatic connectors, and we don't have to redefine every component or all components from scratch. I can select all the components I'm interested in, and yet system will automatically find those connectors for me. I'm pretty much done. I'm all set to start my solve. Again, mesh and solve, and keep in mind that that definition of specific concentrators, mesh concentration around the holes was taken in account, and now you can see how additional components are taken in account that reinforce the structure. Our stress is half of the original stress. As I mentioned, it's quite easy to go and take a look at the results. You can compare them. Let's say I click the first results, you can see the stress at 13.8 versus 6, almost half of the previous stress. So hopefully you can see the power of solid edge simulation when it comes to sheet metal design analysis or plastic, thin wall plastic parts. We can automatically or manually extract mid-surface and save a lot of time and effort analyzing those structures in surface mesh mode. So let's keep going. We didn't talk about an X-Nestron as a solver yet. It's something that happens behind the scene. An X-Nestron gets installed automatically when solid edge is installed. Some people ask, so do I need to get additional X-Nestron seat? No, it all gets installed automatically when you install solid edge. And when you start using solid edge simulation, all the boundary conditions, all the mesh definition will go into this X-Nestron. And after that, as you could see, an X-Nestron will bring results back into post-processing window. It's a very powerful solver. It's an industry-proven solver. A lot of big guys like NASA, for instance, using this solver to analyze their models. and it's quite easy to make sense. So it gives you the progress bar of how far you went through processing your model. Automatic element quality checks is a very welcome addition to that. And in case something goes wrong, you can always take a look at solver logs and see where things went out of hand and how to fix them. Post-processing window is very important. We talked about this for every package, and solid edge simulation really shines here because it delivers to you very flexible post-processing environment where you can take a look at the results in different ways, and you can save them for as a report for further sharing with an organization or with the vendors. It allows you to look at maximum, minimum stress markers, and the bottom line is very flexible environment. Design optimization. This is another tool that allows companies quickly and efficiently analyze their designs and save a lot of effort and specifically material, which leads to bottom line improvements. Because let's face it, sometimes parts get over designed, and automatic functionality that will allow you to quickly analyze and come to a most optimum thickness for your part is really invaluable. So let's take a look at this. The only requirement is that analysis needs to be done. At least one analysis needs to be run in order to perform this optimization. So let's isolate our design. We're going to be doing this on a garage opener assembly, and I'm interested in this garage bracket, in particular garage bracket. Let's open this for analysis. And you probably noticed that already one simulation was already done on this particular bracket. You can see that mid surface was extracted as well because it's the sheet metal component. But what we can do here, we can do optimization, which means system will take care of automatically, will take care of optimizing your model for the optimum condition. First thing, again, everything goes really logically through the process. You can define what you're looking to optimize. In this case, we're looking for mass, obviously, and different options available: minimize, maximize, target, if you have any specific target in mind. In this case, we want to minimize, and then we want to add the limits of, in this case, total transition. That's what I'm looking for. And you can, as a user, you can set the value. Let's say we want to start at 0, and we know that we want to stay below 1 millimeters for total transition. And finally, let's take a look at what we're actually varying. As I mentioned, we can vary multiple parameters. In this case, I'm interested in material thickness. And the system allows you conveniently and efficiently set up the value for this. We know that it needs to be at least 1 millimeter, but we want to stay below 5 millimeters. And then some default parameters that we can take, and finally we can click optimize. So what happened at this point, system will automatically analyze your model, and if you watch closely, you'll notice how the model changes thickness as solid edge simulation processes rip through the process of analyzing this part at different components thickness. And it's really a powerful tool. It's pretty much done. Let's take a look at results. Results are loaded inside of Excel spreadsheet, and you can see that it went through 7 iterations, and it arrived finally at 0.997. Remember, we asked it to total transition not to be more than 1 millimeter, and material thickness for that one is slightly below 3 millimeters. We can take a look at graph, and we can see what the optimum where optimum was reached, and it shows you the graph for all iterations. But the most important that we know, number 7, is our desired result. It's a slightly below 3 millimeters thickness of the material. So let's go back and let's take a look. The important thing is that you can take a look at the results for every optimization. Let's say if we take a look at the plot for the last one. You can see here's our below 1 millimeter displacement, and the thickness slightly below 3 millimeters. But you can take a look at some extreme cases where, for instance, the model was really thin, and this is unacceptable. Obviously, the total translation is 25 millimeters. It will break this part. So how do we implement this? We can go and change the material. Solid Edge conveniently provides gauge information for you. Let's say if we're going to use 12 gauge or maybe 10 gauge. 10 gauge is better than, because with 12 gauge we're slightly lower than we would like to be, but with 10 gauge we overshoot by 0.58 of millimeter, but will be safer, and we can apply to the model and rerun analysis again. So you can see this tool is really speeds up the process of optimization for your part. Solid Edge simulation does it really well for you, optimizing your parts. So the major takeaways from what we just covered. First of all, it's a fully integrated environment. You don't have to step out into different tools. It allows you to design faster and decrease time to market, because you perform analysis faster. You're not waiting for outsourced information or even from results from internal analysts. So you can design better for more competitive products, because again, you shorten time to market. You can define your products faster. You can design your products faster and deliver them to market faster. And you can do more virtual prototyping versus building real prototypes. Instead of 5, 6, we've seen customers building one or sometimes not even a single one, and it greatly reduces costs for your companies. So thank you very much for your time spent with us today, and if you have any questions, I'll be happy to answer them.